So looking at these two triangles today, we're going to be talking about similar transformations and finding exactly what a scale factor would be to find a missing side length. So continuing on, we're looking at similar triangles. Looking at these two, would you say those are similar triangles?
Yeah,
Okay, why? Why do you say those are similar triangles?
I mean, the one, yeah, I mean, then the one's just bigger and then the one's smaller.
Yeah, the angles are the same, and one's just a little bit smaller than the other. So there should be a common scale factor for every side, right? If, say, I'm multiplying by a fourth, so let's look and see what the scale factor is. If I'm starting with ABC and going to DEF, remember, the scale factor is a side length I'm ending with, or a side length I'm starting with, and they just have to be matching sides. So, if I'm looking at this side length compared to this side length, I would have 40 over 32, which I can take 8 out of both of those, so that's the same as 5 over 4. So, if I multiply 24 by 1 1/4, I would get 30. If I multiply 36 by 1 1/4, I would get 45. Okay? So this scale factor works for all three sides. So yeah, they are similar. Would you think any triangle that has a 40 and a 60-degree angle be similar to these two? Yes. Yes, they would. Right? Because as long as I'm keeping those angle measures the same, then I'm just stretching all the sides by the same length, right? Or multiplying them by the same scale factor. Okay, but yes, as you said, if you have a 40 and a 60, then the third one would automatically be the same, right? It'd be 80 degrees for both of those, because there's 180 degrees, and I already have 100 degrees here. So you're right. Any triangle with the same two angle measurements would be similar, because all three angle measures would be the same. There would be some scale factor that I could multiply the starting triangle by to get the ending triangle. All the angles stay the same, you're stretching it proportionally on all sides. So looking at example 1, right? This is just the run through of a proof. There's no notes to take here, although you might want to highlight some things. So following along up here, we're saying if you have a matching angle, two matching angles, would they be similar? Right? And you said, you took a guess and you said yes. Right? This is the proof that they are. So if you have those two matching triangles, there should be a scale factor that you can multiply the one triangle by to get the other one. Right? Dilations preserve the angle measures is essentially the key point behind why they would be the same. Right? If you dilate by something, the angle measures are always going to be the same as what you started with. So if there's a dilation that can map the triangles onto each other, then yeah, they're similar. It follows that if two of the angles are matching, then the third one has to match because they have to add up to 180. So that's called the angle similarity theorem. So the ones that we talked about before, like the angle, side angle, side, we can still use those to say they're congruent. Now we have these similarity theorems that are just saying there is a scale factor that would change one into another. If they have matching angles, you'd say they're similar from AA. Similarly, we have a side similarity. So again, this is just a proof. There's nothing really to take down here. Following along with it. It says if you're looking at a ratio of side lengths, this side compared to this side, and this side compared to this side, and this side compared to the bottom side, if they have the same scale factor, is there a similarity transformation? Right? So remember, the scaling factor is just an end side length of where I started for. So if they have the same scale factor between all three sides, do you think there's a similarity transformation that would map them onto each other? Yeah, of course there would be, right? And it would be that, whatever the ratio is. So it's kind of obvious, but again, this is just the proof saying that if you have a scale factor that you can multiply by to get the other one, they would be similar. So if you have three sides that are similar to each other, similar shapes. If you have two angles that are the same, similar shapes. Okay? And that's summed up right here. Okay, so these are the two we just said, the angle-angle similarity and the side-side-side similarity. This one also follows, right, if you have side, angle, side. If two sides are proportional and the map and the angle between them is equal, then they're also similar. Okay, so these are kind of follow from the ones we've talked before, but again, the ones we were talking about before were for congruent, if they were exactly the same size. Now, if they're similar, that just means one's been stretched. Alright, so how can we make use of this information? So, verifying triangle similarity, we want to know, are the two triangles similar? So, we don't have any angles to go by. Right? Looking at which theorem we would use to prove whether the angles are, or the triangles are the same. We don't know any angle measures, so we have to use the side-side-side similarity one. And again, this just says all three sides have to have the same scale factor. So that's what I need to check on this one. Do all three of those sides have the same scale factor? So I have to match the sides accordingly. Right? So this side AC corresponds to this side FD. So that would be a ratio of,
We on the next page?
yes. And here, it doesn't really matter which one I end with or start with, because if I flipped all these fractions over, they should still be equal. Does that make sense? So I want to see if that fraction is going to be equal to this side compared to this side. So it does 6 over 4 equal. The last one is
Awesome. No, I'm bringing back
Girls.
in the nurse's office before.
and the last one is seeing if this is the same fraction as well. So we need to see whether those ratios are equal to each other. So if you did 7.5 divided by 5, you would get 1.5. Which, if you divide 6 by 4, you would get 1.5. What do you think happens if you divide 4.5 by 3? You get, whoops. 1.5. So the scale factor for all three sides is the same. And again, if you flip these, it doesn't matter if I said I'm starting here and going here. If you flip them over, then it would just be 3/4 as your fraction instead of 1.5. So they're all the same. What can we say about these? Are they similar?
Yes.
Yes. And remember, to write things are similar, we're using not the congruence symbol, but just the accent above. Right? If they have the same scale factor for all three sides, yes, they're similar. Put that little accent between them. Some questions on that one? So looking at the second one down there, same question. We want to know, is PQS and RQP similar? The two triangles share an included angle Q. And so it's kind of hard to see, but if you look, they broke apart the two triangles. And notice that the orientation is different. Right? When they're saying, is PQS similar to RQP, you have to match them up so Q is in the same orientation, right? P is in the same spot that R would be, and S is in the same spot P would be, to orient them, and then compare them whether they're similar. So again, this angle Q, it's the same angle between both triangles. They have the same triangle there. So I have to see if these two sides have the same scale factor, and if they do, this one is also going to have the same scale factor because those angles are the same. So again, it doesn't matter which one I say I tend to begin with. I just want to see if it's going to be the same. So I can say the bottom sides ended with a length of 27, but it started with 18. Is that the same ratio as the side that ended with a side length of 18 but began with a side length of 12? So again, for this one, 27 over 18 is 1.5 again. 18 over 12 is 1.5 again. So they have the same there, the same scale factor for both those sides. So are they similar?
Yes.
Yes. So we're going to say triangle PQS is similar to triangle RQP. And there's one other thing that I left out of both of these. We just have to say which theorem proved that. The first one, we said all three sides have the same, so it would be SSS similarity. This one, we had two sides and the angle between them, so side angle side similarity.
And I have a question.
Yes.
So like I did this question, like I did this one in advance. Like, so I reduced it. So like I got the same fraction. So can I go off of that if I got the same exact fraction that they're equal?
Yes. As long as the fraction is equal. Are you saying like you flip these
Oh no, for the bottom one.
for the bottom one?
Because I got 3 over 2 and then 3 over 2.
Yep.
And I
Yeah.
assumed that was equal off of that.
Yep. Yep. Because that's 3/2 is the same as 1.5. So whether or not you have a fraction or decimal, doesn't matter. As long as it's the same thing. And as long as it reduces to the same thing. So like if you reduce one down to 3/2 and you had another one that's 6/4, it would be the same, right? They both reduce down to 3/2. So you just have to make sure you're fully simplifying your fraction if you're doing it that way. So then this one, we said it's side angle side similarity. Technically, you should put this little accent because it's not side 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 congruence, it's side 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 similarity. Does anyone have any questions or need another second on this? Okay, so applying it here, is triangle ADE similar to triangle ABD? So is this triangle on the left similar to the triangle in the middle? So if I reoriented them so they were kind of matching, I have two even sides and then this long base. So this would be like 1.8, 1.8, 2.4 for the smaller one. And the other one, I have two even sides of 2.4. And then that long side of 3.2. So if I want to see if they're similar, I don't know any angle measurements here, so I have to just go with the 3 ratios of side lengths. So if I'm looking, well, 2.4 over 1.8 and 2.4 over 1.8, those are going to be the same, right? Same numbers, same ratio. So we will really want to see if 3.2 over 2.4 is going to be the same ratio as the other two. You just don't have to write it twice because it's the same thing. And if I do that, I have 3.2 over 2.4 is going to give me 1.3 repeating. And 2.4 over 1.8 is going to give me the same thing. So are those two triangles similar? And side, 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 angle, side, side, side. Everyone would say yes. Side, side, side. And they're not exactly the same, they are similar, so it's side, side, side similarity. Now we're asked, is it okay for me to erase this? Now we're asked, is ADE similar to BDC? Actually, I could have left my work there. I don't think we need to redraw these ones. Is this triangle on the bottom right similar to the one on the left? Comparing sides to sides. They do have they have the same side here. Right? They share the same angle there, but then the adjacent side right after that, it's a different size. So no, right? Really close to being similar. Well, they're really close to being exactly the same, right? But because these have the same sides, the same angle, but then a different side, then these ones are automatically not similar to each other. So for number 2, I would say no. And it's because it doesn't have the same scale factor between all 3 sides. Or you could say 1.8 does not equal 1.4. And there's no okay. So finding lengths in similar triangles, if I know a scale factor and I'm missing a side length, I need to know how to use the scale factor to find the side length. So we want to know what is the length of MN. So we want to know that length there. And so if I know that these sides are equal, these sides are equal, these angles are equal because they're across from each other. So by side angle side, these are proportional to each other. So if I want to find out what this side length is, I need to know what is my scale factor between these two. And with these problems, I don't know, you don't really know which one you're starting with. It doesn't really matter which one I'm starting with. If I say I'm starting with this one and going to this one, I started with a side length of 1 and ended up with a side length of 75. So what did I have to multiply by? 75, right? But if I was going the other way, if I say I started with 75 and ended with 1, it would have been 1/75th as my scale factor. You would just multiply that by 10 instead of finding out what do you have to multiply by 75 to get 10. If that's confusing, I'll do it too. But, so my scale factor is 75. So essentially the question is, what do I have to multiply by 75 to get 10? Or what is 10 divided by 75? How I would write this problem out though, so we can write this a ratio of sides. I'm going to call this side mn x, just for the universal variable we're always trying to find. So that side length x, I started with a length of 10. And that ratio is equal to the other one. Here, I started with 1. Let's say I ended with 1, and I started with 75. Those two ratios have to be equal. This side compared to this side has to be equal to this side compared to this side. Now, if you were solving this, what would you have to do? How would I solve this? What's the first step? What's that? Well, you could type that into a calculator and find out what 1 divided by 75 is. But if you had x divided by a number, how do you undo dividing by that number? You multiply by what you're dividing by, right? So if I'm dividing by 10, I'm going to undo that by multiplying by 10. So if I times this side by 10, I need to multiply this side by 10. And that gives me, so over here, that's going to cancel out. I have x equals 10 times 1/75th. Remember, if you're multiplying a whole number times a fraction, you only multiply into the numerator, right? This is the same thing as 10 over 75. So you could leave it as 10/75ths if you wanted. Oh, well, you should reduce it to. Yes, 10 over 75. Which if you factor 5 out of it, you get. So this side length is 2/15.
Can't you just simplify that? Like 7.5?
It would be 0.13 repeating. If it was split, it'd be 7.5. Any questions on that? Because that's used a lot. Okay, you'll see these kind of problems a lot, and they like to put them as word problems. So if we're looking at this one, Avery puts up a radio antenna. Ella tells them that their city has a law. Towers can't be more than 50 feet in height. We want to measure the length of the shadow and compare to see what the actual height of his tower is. And these two triangles are similar. These shadow problems, they are similar because if you're comparing your shadow to the object of something else, you're always going to meet the ground at a 90 degrees angle. And whatever angle the sun's hitting that object at, it's going to hit you at the same object, or at the same angle, and it's going to make the same angle with the ground. So, we know, because the angles theorem, that these are similar, so there's some scale factor to get this smaller triangle to be the larger one. What is that scale factor if I'm starting with a side length of 5 and I end up with 40? What did I have to multiply by?
8.
8. Right? That's his scale factor here. So scale factor is 8. So there's two ways of doing this problem. You can find out what the scale factor is, and then think about how you would apply that scale factor. So how would I apply the scale factor? If I'm multiplying by a factor of 8, how can I use that information to find out what the length of this tower is? What would I have to multiply by? 6, right? Scale factor is 8, so the tower has to be 6 times 8, which is 48. So it's 48 feet tall. Now, if you want to solve this just like the one we just did, setting it up as a math problem, I don't know what this side length is, but I know that this side compared to this side is the same as this side compared to this side. So x over 6 equals 8. Multiply those sides by 6. You're going to get 48 again. Right? So you could have solved it this way, setting up just the ratio of sides have to be equal. Or if you find that scale factor and know how to apply it to the problem. Either way, it's going to give you the same thing. Yes. Yes. Give me 1 second. All right. If the tower were 50 feet tall, how long would the shadow of the tower be? So, if the tower were 50 feet tall, and I wanted to find out the length of the tower, 5 and 6. You'd be solving this the same way you could find the scale factor, or you could set up the ratio of sides. This side compared to this side is the same as this side compared to this side. And again, if you're dividing by something, multiplying by 5, so in this case, x would be 250 divided by 6, which is 41.6.